Okay, this chart should look familiar to you because we looked at it in our previous lesson when we were interested in the various structures that make up our universe. So our goal today is to figure out how did astronomers arrive at all of those numbers that are in that chart. So our first method is going to be called radar imaging, in which we're going to use a light beam, could use radar, but we're going to use some kind of light. We're going to bounce it off of an object, and then it's going to come back to us. We're going to use that time it takes in order to figure out how far away the object is. So, got an object here. Going to take our flashlight, point it at the object. The instant we turn on the light, we click our stopwatch. We wait for the light to reach the object, bounce off of it, come back to us, and then click the stopwatch again. So we're going to make use of the fact that speed, v, is going to be equal to distance r divided by t. So that's our definition of what speed is. So if we rearrange this, we get that distance r is equal to vt. Now, if we're using light waves, then the speed of light is what we're going to use for the letter v. So now we're going to change this so it says speed of light multiplied by time t. But if you look at the formula, you notice that it has a 2 on the bottom. So where does that 2 come from? Because what we really need is the amount of time it took to go from the flashlight to the object. But what we actually measured with our stopwatch was the time to go there and then to come back. So we need to take this total time here and divide it by 2 in order to use the formula. Okay, now this formula, this method of measuring distances is only useful for inside of our solar system. Because let's say that we, even if we could, measure the distance to Alpha Centauri, so the planet that, or the star where Zefram Cochrane came from in Star Trek. Remember him? All right. So we point our flashlight at Alpha Centauri, we click it, we click our stopwatch. Well, Alpha Centauri is about 4 light years away. So that means it's going to take the light beam about 4 years to get there, 4 years to come back, so it's a grand total of 8 years. So that would mean we'd have to run our experiment for 8 years in order to get any results. And so that's just not very practical. So it is practical, though, to use this inside the solar system. Let's say that we want to measure the distance from the Earth to the Moon. So it takes 2.56 seconds for a light beam to bounce off and return to the Earth from the Moon. How far away is the Moon? So we're going to write down what we're given and what we're looking for. So we were given the total amount of time, 2.56 seconds, and we were given the distance, we're looking for the distance. So we're going to take our time, plug it into the formula, equation 20.1, insert 3 times 10 to the 8th meters per second for the speed of light, and then solve it, and it turns out it's 3.84 times 10 to the 8th meters. So that would be the distance from Earth to the Moon. So that's an example of how you would use this particular technique to measure a distance. All right, we're going to take a break, and when we come back, we're going to talk about stellar parallax.